Hello, welcome back to MEC 416/816 Engineering Acoustics. In this lecture, we're going to continue our discussion of single degree of freedom harmonic oscillators, and we're going to focus on the energy of vibration. Before we derive the energy of vibration for a single degree of freedom harmonic oscillator, I want to just talk about mechanical and total energy. So mechanical energy is defined as the summation of the potential and kinetic energy. And it's an energy that is conserved when there is no damping and no external forcing acting on the system. So this is conserved with no damping and no external forcing. The total energy is the summation of the potential, kinetic, and dissipated energy. So the energy dissipated by the damping of the system. And in this case, this is conserved when there is no forcing acting on the system. So it's conserved with damping, provided that there is no external force. If there's an external force acting on the system, then it's no longer conserved, and in which case you would have to incorporate the work done to the structure by that external force, and then you would be able to apply the first law of thermodynamics. All right, so to find the energy of a vibrating single degree of freedom system, we're going to start with the governing equation of motion. We're going to look at a forced one in this case. We have mx double dot plus bx dot plus kx is equal to some forcing function f of t. It says 13 here. This should actually say equation 51. So we're going to multiply equation 51 here by x dot, and then we're going to integrate with respect to some dummy variable tau for time. All right, so to do that, let's just simply do that. So we're going to have the integral from 0 to t for m of the quantity mx double dot x dot plus kx x dot, all of that, times d tau. And the reason I've grouped these two together will become apparent in a moment, is because this gives us the mechanical energy, plus the integral from 0 to tau, in fact, sorry, that should be 0 to t of b times x dot squared d tau. And that's our dissipated energy, and this is equal to the integral from 0 to t of x dot times f of t d tau. And that right there is the work done on the system. So, like I said, this will end up being our mechanical energy. Let me rewrite that. This is our mechanical energy. This middle term, that's our dissipated energy. This term on the far end is going to be the work done by that external force. Okay, we're going to do the integral for the first two terms, and then we'll talk about the integrals for the second two terms. Okay, so let's do first the one with the x double dot term in it. We can pull an m out of the integral, so we'll get m times the integral from 0 to t of x dot, x double dot times x dot, d tau. This will be equal to m times the integral from 0 to t times the derivative d over d t, or d tau, in this case actually, d tau times the quantity 1/2 x dot squared d tau, which ends up being equal to the quantity 1/2 m x dot squared minus 1/2 mu sub 0 squared. That's our initial velocity. and that you can see this now the standard form for kinetic energy, which we'll call big T. That's just a standard that's used to define the kinetic energy. We can do the similar thing for the term with a kx in it. So k times the integral from 0 to t of x dot x d tau. That's then equal to the integral from 0 to equal to k times the integral from 0 to t of the derivative d over d tau, 1/2 x squared in this case, d tau, which then is equal to 1/2 k x squared minus 1/2 k x 0 squared. That's our potential energy, which we can call big V. Okay, so you can see how the two terms, let me go ahead and underline them or circle them with a laser. You see how these two terms now led to the mechanical energy, whereas the middle term is our dissipated energy and the last term is the work done. All right, so let me just talk about the two integrals that remain. The one for the dissipated energy, we do not know how to solve it. By we, I mean like the human species has not figured out how to solve that integral yet. And as a result, you end up having to compute that numerically, and rather than you can't compute it analytically. Well, we don't know how to compute it analytically, at least. The integral on the right depends on f of t, and so in this case we're considering just a generic f of t, and so we can't compute that directly until we know what f of t is and we know what x dot is. Once we know those two variables, then we can compute that, and typically we'll compute this numerically as well. Okay, so to summarize what we've looked at so far, we can say that the mechanical energy of the oscillator, let's call this E of t, is equal to 1/2 mx dot squared, that's our kinetic energy, plus 1/2 kx squared, that's our potential energy, minus that initial energy E0. And of course here E0 is equal to 1/2 mu0 squared plus 1/2 kx0 squared. The work done, we can call that W of t. That is equal to the integral from 0 to t x dot times f of t d tau. And then the dissipated energy, I like to use big D. That's equal to the integral from 0 to t of b x dot squared d tau. Okay, that is what I wanted to say with mechanical energy, with the energy of vibration. In the next lecture, we're going to cover mechanical impedance.